Hello, my name is Quirijn, and in this video we'll be talking about type deduction in C++. A topic that you usually don't need to think about, because things tend to work just as expected. Until they don't. Especially as you start writing more generic and reusable code using templates, you're bound to run into situations where not fully understanding type deduction could result in strange errors, or even worse, code that compiles just fine, but then when you run it turns out to behave different than expected. Let me give you an example. Here we have a custom container class, myContainer, and it's secretly just a simple wrapper around standard vector. I created this container class because I want to abstract from this design detail, allowing me to more easily swap out the std vector for other underlying data types later. myContainer supports all kinds of operations, but to keep things simple, I'm only showing the definition of the subscript operator here. This operator allows the user to retrieve the elements stored at a certain index by reference. And this allows me to write the following code. I can declare an instance of myContainer of int, and then after everything's initialized, I can, for example, retrieve the element stored at index 42 and assign 10 to it. Now, if you compile this and run it, it all works fine. But what if we, instead of making a container of ints, would for example make a container of booleans? Something like this. Then suddenly, if we try to compile, we get an error. Error: cannot bind non-const lvalue reference of type boolref to an rvalue of type bool. So what's going on here? Let's check how the vector of bool is defined on cvpreference.com. So here we find that vector of bool is different than other vectors, because it uses some space-efficient way of storing the booleans, basically using only a single bit for every value. But since you of course cannot return single bits, the reference type, which is what is returned from your subscript operator, actually returns a proxy class. And this proxy class is of course returned by value. So getting back to our error, when we fill in the template parameter of bool, we see that our return type should be something like this, a reference to bool. That's this non-const lvalue reference of type bool in the error. The thing that's returned when accessing mdata is a standard bit reference, and that's returned by value. So this is our rvalue, and this thing can be implicitly converted to a bool, which the compiler does in an attempt to match it to our desired return type, and that's what gives us this rvalue of type bool. So now that we understand what this error is telling us, how can we fix the problem? One solution might be to try and use the auto keyword instead of explicitly specifying the return type. And now suddenly everything compiles and behaves as expected. This is because this auto type is deduced to be the exact same bit reference proxy object that's returned when using the subscript operator on mdata. However, if we now go back to the container of int example, we run into problems again. Error: lvalue required as left operand of assignment. And that's because auto here is deduced to be an integer, not a reference to an integer. So we could add an ampersand here, but then we can run into problems with our boolean container. The solution is to use decal type auto, because yes, this deduces to something different than just using auto itself. This simple example shows how you can run into problems with type deduction when writing generic code, and how tricky it can be to find the correct solution. That's why in this two-part video I'll explain everything you need to know about type deduction. My name is Quirijn, and you are watching a Bits of Q Advanced C++ tutorial. Let's get started. First of all, where is type deduction used? This depends a bit on which language version you're using. Back in C++98, the answer to this question was quite simple. Type deduction was only used for templates. But in C+11, it's all over the place. We got auto, forwarding references, lambdas were introduced, and even decal type. All of these require type deduction. But that's not all. In C+14, we got auto return type deduction, which is demonstrated in our motivational example. The lambdas were also made more powerful, allowing generic lambdas accepting auto as their parameter, and allowing for lambda init captures. In other words, understanding type deduction is increasingly more important in modern C++, especially if you want to write generic code that has high performance. This video is the first part of a two-part tutorial on type deduction, covering everything you need to know about the topic. In this part, we'll cover template type deduction, auto type deduction, and with that, also the rules for forwarding references. So let's get into it. I have a template function, func, declared here, and a call to that function with a certain expression. When talking about type deduction, we say that t is the deduced type. And this tref here, that's the type of the parameter. Using the expression, the compiler deduces both t and the parameter type. The type that is deduced for t depends on the parameter type. For example, say I have a constant integer a and I pass this a to func. In this case, a is the expression. The compiler will now apply the rules of type deduction, which we'll explain in detail in a bit, to find that the parameter type is a reference to const int, and based on that the deduced type, t, is const int. When talking about template type deduction, there's three different cases that we distinguish. First, when the parameter type is neither a reference nor a pointer. So this is when you're passing things by value. The second case is when your parameter type is either a reference or a pointer. And the third case is when your parameter type is a forwarding reference. If you're unfamiliar with forwarding references, I recently made an episode on perfect forwarding where I explain what forwarding references are and how they can be used. I'll leave a link in the description. So, let's start with the first case. Deduction for by value parameters. Determining the type in this case is quite easy. First of all, if your expression's type is a reference, we simply ignore that part. First of all, if your expression's type is a reference, we simply ignore that. Secondly, if your expression is either const or volatile, we also just strip those out. As an example, I have an integer x here and a reference to a const int, rcx. If I pass x to my function, the parameter type as well as t gets deduced to be an int. If I pass my reference to const int, rcx, we get exactly the same output. Both the reference and the const part get ignored. Lastly, if I pass an r value, we again have the same result. Both parameter type and t are integers. Now there's one little nuance here. That's about this const part. Remember, there's a difference between an expression that is const and an expression containing const. This is something that only really matters when you're dealing with pointers. For example, here p1 is a pointer to a const int. In other words, an expression that contains const. p2 on the other hand is a const pointer to a const int. Meaning that the expression itself is const. You cannot, say, direct the pointer to point at something else, nor can you change the thing the pointer is currently pointing to, because that's a const int. Lastly, p3 is a const pointer to int. The expression itself, the pointer, that's const. You again cannot assign it to a different piece of memory. But the thing is pointing to, that's just a normal integer. That's something we can modify. And the rules for type deduction state that only the top level const is removed. If I pass my pointers to this function, the first two give the exact same result. The parameter type is just a pointer to a const int. That's because this top level const of p2 gets stripped off. The third pointer, that is a const expression, but it's pointing to something non-const. So in this case, we see that our parameter type is just a pointer to int. So that covers passing by value. Secondly, we have the deduction rules for references and pointers. Just like with values, if your expression is a reference, we ignore that part. And then we simply pattern match the expression against the parameter to determine t. So again, we have an integer x. Now we also have a const integer, cx, and the reference to const, rcx. If we pass x to our function, the parameter type will be a reference to int, and t itself will just be an int. This is what I mean with this pattern matching. If we pass a const int, parameter type will be a reference to const int, t itself will be just const int. Lastly, if I pass in a reference to const int, we see that our parameter type is also referenced to const int, but t is just a const int, not a reference. So even though we're passing in a reference, our t itself is not a reference. The third set of rules covers the case for forwarding references. This one is slightly more complicated, as it distinguishes between lvalue and rvalue expressions. If you're not familiar with lvalues and rvalues, I'll leave a link in the description to my video on move semantics, where I explain what these things are in detail. If your expression is either an lvalue or an lvalue reference to some type e, then t is deduced to be an lvalue reference to e, which means that the type of our parameter is e_ref ref. This is of course not valid 0+, and hence this invokes the reference collapsing rules, which we discussed in our forwarding references episode, leading to the final type that's deduced for our parameter type to be an lvalue reference to e. The second case is if your expression is an rvalue reference. In that case, we just ignore the reference part and do some pattern matching, just like when you're accepting by reference. So let's see this in practice. I got my integer x again, and I got my reference to const int rcx. So these are the two lvalue cases. So in this case, both the parameter type and t will be lvalue references to either int or const int. When on the other end we pass an rvalue, such as this 42, then the parameter type is an rvalue reference to int, but our t itself, that is just an integer. It's something important to keep in mind while dealing with forwarding references. Together, these three cases, accepting by value, accepting by reference, and accepting by forwarding reference, cover the rules of template type deduction. The second thing I wanted to discuss was auto type deduction. And here I have some good news. Type deduction when using auto works the same as template type deduction, with the exception of one special case. If I have a template function like this, and I would try to pass a braced initializer list, then I would get a compilation error. That's because a braced initializer list does not have a type, so there's no way t can be deduced. But strangely enough, if I try to do a copy initialization of an auto variable, like this, x's type would actually be an initializer list of integers. To make things more confusing, this only works for copy initialization. If I try to use braced initialization, I'll just get a compilation error. Okay, now this was a lot of information, so let me try to summarize this in a nice table. Top of the table, we have the different ways of accepting your input parameter: by value, by reference, and by forwarding reference. Then on the left, we have the different ways of passing our expression: a by value expression, an lvalue reference, and an rvalue reference. I'm using the question marks here next to auto to indicate that this should be either nothing, a single ampersand, or 2, depending on which column you're looking at. So, looking at the case where we accept our parameter by value, the first column, we see that regardless of whether our expression is a value, an lvalue reference, or an rvalue reference, we always deduce int. That's because in the by value case we have this rule about just stripping off reference, top level const, and volatile. If we accept our input by lvalue reference, then in both the value and lvalue reference expression case, we see that our parameter type, as well as the type of the variable a, become an lvalue reference to int, but the deduced type t is just an integer. Of course, if we try to assign an rvalue reference to an lvalue reference, we get a compilation error. In the last column, we look at the case where we accept our input by forwarding reference. And here we see this distinction between where we pass an lvalue expression or an rvalue expression. Both the value and the lvalue reference case, we see that our t as well as our parameter type becomes an lvalue reference to int. However, when we pass an rvalue, then our t is just the value type int, whereas our parameter type becomes an rvalue reference to int. Which means that this is our full table summarizing everything you need to know about auto and template type deduction. I hope you enjoyed the episode and learned something new. If you did, make sure to leave a like. And remember, this is just part 1. In part 2 we'll talk about the other types of type deduction, such as auto-return type deduction or lambda init captures. If you're not yet subscribed, make sure to hit that button now so you don't miss out on the next episode. See you next time.